about some of the work I've been doing over the last few years, or have been doing in apostology at MRC, in terms of thinking about pump probe processes in 20-second ionization studies. So a lot of this introduction has already been given today, so I can skip a little bit through some of these slides, but just to say that the kind of processes that we're going to be talking about are essentially dynamics on excited states of essentially molecular dynamics. So we're normally interested in our lab in thinking about larger systems, things we've talked about so far, thinking about molecular dynamics. And so we have just a regular kind of pump probe scheme here. We're going to pump up, prepare some excited state, there's going to be some dynamics, and then we want to probe that in some way. And this probe really could be anything, but I'm specifically going to be talking about photoionization. And so we'll be thinking about time-evolved photoelectron spectroscopy, time-evolved ion emission spectroscopy, angular distributions. We can think about correlated observables in the case where we make multi-dimensional measurements. So there's various possibilities there. And so the reason that we like to draw this stick figure, this stick diagram, is because we can make a lovely analogy with photography that everyone likes to make, and really we're just going to project out the dynamics that we're interested in onto the ionization continuum or via whatever other probe we're interested in using, and we're going to follow these dynamics directly in some way. So people like to talk about making a molecular movie and things like this. And so sometimes this can be a very nice picture, and this metaphor kind of holds. And so particularly we have simple or low dimensionality systems, or equivalently somewhat low dimensionality observables. And so there's a nice case that a simple wave packet in sodium dimer here oscillates back and forth. You can calculate how it looks, and if you go and measure the photoelectron spectrum, you can basically just follow these oscillations and tie that into just the bond length, just this vibrating motion of the molecule. And Marcus also showed us a very nice example this morning where if you go to a system where you have a big enough probe photon and you can sit and monitor a particular band in the spectrum or a particular stage, you can see a band, a signal appear, and you can associate that with the process you're interested in. So in that case, you have a probe that's very well suited to the dynamics you're interested in studying. More generally, so for complex systems or complex observables, things get, well, more complicated, as you might expect. So in terms of photoionization, if we're thinking about the dipole matrix element that's coupling this wave packet we've prepared into the ionization continuum, we're coupling some wave function here onto the compound state as opposed to the photoion and photoelectron. And in particular, the electron is going to be a complicated beast. This is a continuum scattering function that we have to deal with. And this is essentially just kind of writing this in a wave packet type expansion. So if you have now this initial state, or prepared state wave packet expanded in some basis set, and you have this bunch of complex time-dependent parameters projecting out into the continuum. So this is going to be a complicated thing. Additionally, I haven't written it here, but you could also have dynamics in the ion, or you could have multiple ionization events creating some interferences in the continuum. So there's lots of interesting things that could go on. And so this is the optimist or pessimist test. So this is either very interesting, there's lots of interesting physics we can think about monitoring and learning about, or this is very disappointing because it's not very direct. And so if we really only wanted to learn about excited state dynamics, then this is going to be a tough proposal. And so this is sort of a nice example I'd like to use to make this point. This is some work from Vince McCoy's group, 2010 paper where they were looking at NO2 dynamics. And so you can see already this looks like a complicated system. There's various coupled states here. The wave packet does something complicated. And you project this out against the photoelectron spectrum. And you can see there's a bunch of blobs, everything kind of, these are different channels plotted here. Everything gets overlapped, it becomes horrendous. And of course if you calculate this, that's no problem. You can separate out these different contributions, you can understand what's going on. If I went down to the lab and measured this, well, you wouldn't know where to start. So that makes things tough. And it also makes the point I think was already been made today, that it's nice to have a bridge between good theory, good high quality theory, and experimental work, which, so hopefully my talk will show a little bit, we're now getting to the point where we can do some of these calculations on reasonably large systems and get good comparison with experimental results. And then just to further make the point, if we went and measured the angular distributions from this system, these also show very complex behaviour. So this is, again, I'm not going to go through the details, but this is just to show that various different channels, the total angular distribution onward measure as a function of energy and time is both a complicated, hence interesting thing. So conceptually, I'm not telling you anything you don't already know. But I think we are getting to the point where with multidimensional experiments and also with improved calculations, we can start to really make some leap forward in the complexity of the systems we can treat to a reasonable level of accuracy and go beyond sort of, I guess, it's particularly been the case in chemistry, go beyond often very sort of general hand-waving models of how some dynamics is occurring. And I'm going to try and go through 3 examples of this, talking primarily first about rotational wave packets, and then also about vibronic couplings and vibronic wave packets in more complex systems. So just a roadmap then. Rotational dynamics I'll talk about first. Vibronic dynamics in CS2. So this is the case we've got furthest with so far in terms of both experiment and theory. Some recent experimental work on butadiene, but I don't run out of time at that point. Okay, so we were driven to do some work on rotational wave packets because we did some experiments that we didn't understand. And this is again a kind of an interesting area because much of this work has been done and the physics is understood, but the application and the sort of the bridge between experimentalists working in the lab and the theory work was not really there. So we ended up spending a little bit of time trying to sort of really piece that together. So in this case I'm going to be talking about just preparing a broad rotational wave packet with an infrared pulse, so the normal kind of impulsive alignment techniques that one would think about. And I'm going to mostly be considering the rotational wave packet just in terms of the axis distribution, so essentially the projection of this wave packet we prepare onto some spatial axes. So that's going to be used to define the alignment of our ensemble of molecules. And the case we were actually interested in was butadiene. So I mean, I'm using this as a general example, but this is a specific calculation for butadiene under these laser parameters. And the first obvious thing is that this axis distribution has complex time dependence. We have characteristic variables that are well known at around half a level here, up to 60 picoseconds in this case. But what's not often thought about is all this other graphs that you see out here. And also, in some cases, the exact form of this half revival. And the reason that you may or may not choose to think about these extra characteristics is because it depends on your observable and whether these things are reported or not. In this case, I'm going to tell you that they are. So another way we can think about this distribution, maybe this is what you're more familiar with, is just thinking about the expectation value of cos squared theta. And this is essentially just the lowest order moment of that full distribution that we saw on the last slide. And so that shows some characteristic wiggles. And you can see immediately that it's pretty flat away from this revival. If we think about parameterizing this distribution more generally, we can talk in terms of this expansion in spherical harmonics with these AKQ parameters. And this is just another way of expanding this angular distribution, this axis distribution. And the lowest order term here with k equals 2 is just essentially the same as the cos squared theta term that we used to, and then higher order terms, so different k would correspond to higher order cos n terms. And then we can also in this description describe non-cylindrically symmetric systems. And so then this is just proving to you here that the A20 looks the same as cos squared theta with slightly different values. So that's the second order moment. So now if we were to look at higher order, we get the interesting things again. So this is showing various values of k, and we only have even terms in this case, q equals 0, just split into batches of 10 here. And so the immediate thing you can see, even just looking at 4 and 6, it's kind of a jumble and a bit of a mess on here, but you can probably kind of believe me if I tell you that if you look at k equals 4 or k equals 6, they kind of come up in this dip that we would see in k equals 2 at the half revival here. And they also show kind of some oscillations and some revival features out at different times. And so if you went down to the lab and you measured some observable that wasn't just dependent on cos squared theta but had these other terms mapped into it, then you sort of would want to know about this and understand this, because otherwise you're not really going to be able to optimize or characterize your aligned distribution that you prepared, which is normally the first step towards going and doing some experiment where you're hoping to record observables approaching the molecular frame. So this is kind of the potentially important. And so I said in this case I'm going to be thinking about observables in ionization. So we're going to specifically talk a bit more about the photoelectron angular distributions, which again just essentially a photoelectron flux in spherical polar space. So we can expand that with these beta parameters as a spherical harmonic expansion. And we can think about this as a convolution of essentially the molecular frame result, so the molecular frame angular distribution, with this alignment distribution, these AKQ parameters. So there's quite a lot of complexity hidden in this other term here, but we're going to ignore that for the time being. Talk about that later. And we can also think about making measurements in a rotated frame. So for example, if one were to measure the ionization yield as a function of pump probe geometry, and that essentially has a similar form, but just with an extra rotation matrix element in there. So that's this kind of geometry shown in the corner here. And I should also mention that the L equals 0, M equals 0 term here is essentially the ionization yield. So beta 0, 0 we're going to use to determine the ionization yield in these cases. So initially this is just what you would get if you calculate this for various photon order processes. And I probably should have mentioned at the beginning, but I don't think I did that. I'm really considering mostly weak field work here. So just a few photon order processes, but this should scale up at least phenomenologically to strong field measurements also. And so for an n-order process, if you go through the algebra and go through the angular momentum coupling, you can say that axis distribution moments of up to 2n can couple into this yield. And so if you went and measured the yield for a 2-photon process or a 3-photon process, you can see that these extra features start to appear in the yield that you would measure, which corresponds to coupling in of higher order axis distribution by higher order k terms. You can also think about measuring the angle resolved ionization yield, so that was what I was mentioning with this little schematic here before. And so this is the case where you measure the yield as a function of pump probe polarization geometry. And so this is shown in polar form as a function of angle and time in these plots. And so again, you can see if you go 1 photon, 2 photon, 3 photon, you start to see extra angular features appearing as you go around any of these time slices, and also extra oscillations appearing temporally, again as you couple in these higher order terms of distribution. And so this thing here is the initial distribution that we're preparing. And so you can kind of see what you might expect, which is if you move to higher photon orders, you start to get something, or start to map something that more closely resembles the full axis distribution as opposed to just that cos squared theta expectation value, for instance. And so if one were interested in really mapping rotational distributions, this may be a good observable to use. I guess another thing to take out of this picture is that if you're proposing to do an experiment to measure a molecular frame property, then your cos squared theta alone is not really telling you precisely how this distribution looks, and it may actually be much more aligned than that parameter, that metric suggests.
Can I ask, why do we make a point out of this? Because I mean, any theoretician would of course just calculate the distribution and put the correct distribution and not use cosine squared.
Any theoretician could, yes. Yeah. Many experimentalists don't.
No, but I mean, it's here you have to use the correct distribution.
Yeah, sure. Yeah. I mean, I'm making this point because, as I say, in the literature, this is well known.
The measure is cosine squared. That's clear. I mean, this is just. For tradition, this has been the measure for how well aligned the distribution is.
Yes,
so this is what everybody is studying.
Yes.
So of course, if you want to, calculate anything or understand,
you
use
the
correct one.
Yeah. But I mean, the point I'm making here as well is that these couple differently into different observables. So the reason I came to this is because we were doing work in the lab where we were measuring things we didn't understand. Of course, we were trying to understand everything in terms of cos squared theta, and this is what's immediate. This is the first go-to thing. So this is just kind of to make the point more about this coupling into observables. I mean, I agree. If you're doing this correctly, if you're the theorist, then you put all of this in there, for sure. I don't deny that. So following that point, I should reference these two papers, which again, particularly the work from Tamar Seidelman's group, has shown a lot of this kind of has done a lot of this work in terms of the photoelectron angular distributions. So this really is a reiteration of a lot of these points and just trying to put them together in a more digestible manner, particularly for experimentalists. And so finally, this is just showing now the photoelectron angular distributions, so the yields and also the various different beta parameters that one would measure as a function now of the relative parallel and perpendicular ionization yields. And so we care about this because for any given molecule, you're going to sit kind of somewhere in this range where parallel and perpendicular ionization yields may be very different or may be very similar. And so again, particularly from the experimental perspective, if you're in the lab trying to measure this time-dependent yield and trying to optimize some aligned ensemble, it's kind of important to know whereabouts on this plot you actually sit, because if you're right in the middle here, you really have no contrast. So this is kind of again, important if you're trying to understand and measure these kind of distributions. And again, the higher order terms will again map these higher order alignment parameters. Okay, so that's just a brief summary of that. And so, again, the last, I already put it on here. That was my point. And I should also say, actually, so again, the reason this was important was because we were trying to make molecular frame measurements of photoelectron angular distributions, and so we cared, again, precisely about how our distribution looked, but also how practically we could go down to the lab and optimize the distribution we were preparing. Okay, so let me move on to something that's a bit newer, a bit more interesting perhaps for us. Every comment's directed to you now. So let's talk briefly about this CS2 experiment. So actually the experiment's not that new. This is from a few years ago, and this was already published in 2009. And the concept here was to do exactly this kind of molecular frame angular distribution measurement as a function of time, so to see whether we could monitor molecular dynamics with photoelectron angular distributions, and in particular to try and think about whether we could think of them as an observable that was very sensitive to the electronic structure, as opposed to the vibrational motions, which typically are going to show up more in the photoelectron spectrum. So this was indeed an alignment experiment. A two-component wave packet was more or less cleanly prepared. So this is how the absorption spectrum looks. And we basically sit on these two lines and pump up to an excited state. And then we ionize with a time-delayed probe pulse and measure the photoelectron angular distributions, essentially. So conceptually, it sort of looks something like this. We prepare on this excited state that sort of sits on this ridge here. And you can imagine that the wave packet is kind of going to roll down to the bending coordinate, so we're going to see some significant bending motion. And similarly, the wave packet can also roll off this way, go towards dissociation. And so this fits with what you see in the absorption spectrum, actually, that we have very strongly coupled motions with the asymmetric stretch leading to dissociation and the bending motion mode being essentially bound. And then as a function of time, we're going to think about the angular distributions showing some characteristic behavior of this wave packet. This was the instrument it was recorded on. I won't say too much about it, apart from this is essentially a dual flat field imaging machine. We can do 3D imaging of electrons on this lower time collision sensitive detector, and similarly for ions on the upper detector, and we can measure in coincidence and do things like this. And so in this case, this was the spectrum observed, and so you see it kind of looks like a maybe slightly uninteresting blobby thing. But there is a quantum beat in this lowest energy channel, which is to be equal 0 in the ion. So we're going from this highly excited state to be equal 0 in the ion. You see an initial fairly sharp signal, and then you see some recurrence here, some revival. And if you look up some of these different energy slices, you can sort of see there's a little bit of oscillatory behavior here, but it's not very strong. It's hard to see it. And you can do a global fit to this, and you can put out some time constants. In this case, we see 70 femtoseconds, so it's fast time constant, 830 femtoseconds, longer time constant, and a beat period of around 80 seconds. So those three energy slices that were highlighted there, shown again here, just integrated over those ranges. And again, this just basically reiterates the behavior that I just said, that you can see as you go for this highest electromagnetic energy slice, this is corresponding to V equals 0 in the ion. You see this oscillation, this beat, and this is the beat component with a fit, this blue line here. And as you go to these lower energy slices, this beat goes away. If you look at the angular distributions, on the other hand, this beat is consistently seen across all three of these energy slices with increases in the polar distribution. And so in this case, these all look a bit different because there's energy dependence also in this observable, so it makes it a little more complicated. But it does start to hint that really we're seeing essentially the electronic dynamics projected out here, because we're only going to a single final electronic state, and we're not seeing the kind of blurring that we get from going to multiple vibrational states, which gives this broad band in the spectrum at lower energies. So you can press me on the details of this later, but essentially you can more or less take away from this that the pads are dominated by electronic evolution, and you can theoretically sort of say this as well. It's not totally rigorous, but as a first approximation, it's a good way to think about this observable. And it's, in any case, certainly very different from just the energy result spectrum. So the first thing we did with this was try to model it a little bit, just to try and make some beginning of a bridge between experiment and theory. And so in this case, we modeled things just basically with a two-state model, based on the electronic state mixing, and the known peak-second beat period. So this is essentially the spacing of those two features that we prepare in the absorption spectrum. And that gives a reasonable result. We see something where indeed this angular distribution beats, and it has an increase in flux at the poles at around 500 femtoseconds. But this is not really that satisfying. It's a step in the right direction, but it's kind of telling us that we have the right idea in the physics, but, well, I'm generous if I call it semi-quantitative. Let's call this qualitative, because we don't really know the details of either the wave packet or the matrix of the ionization matrix elements. So we can now go a bit further. We have some full dynamics treatments and ionization matrix elements, and so this is work, specifically the dynamics is done by Michael Skirman at NRC, and also Vince McCoy's group have been doing the matrix element part of this calculation. And so now we can really think about doing both the full wave packet and the full ionization calculation. So let me just show you how the potential energy surface looks again in this case. So I think I already described this. We basically have, this is the state we populate with the prompt pulse, and we have some complicated dynamics going on in this state. And there's also this state just above that coupled into a conical intersection. So you can imagine that around this region in coordinate space, there's going to be a significant change in the electronic character. And then we can also head out to dissociation, then this second conical intersection. What kills us in this experiment is that we have a really small observation window. And so again, this is sort of, Mark showed a nice example of going to a very high energy photon to get around this problem. Here we only have our tabletop laser source, we're working in the UV. And the observation window, actually, when you go to calculate how the ion surfaces look, is really, really small if you're just doing one photon ionization. And really, we can only see motion essentially along this bending period. And so this is the kind of thing that you don't think about until you actually make the effort to go and calculate these surfaces. And again, it was not obvious initially in the experiment that this would be an issue. And I guess, again, I bring this up kind of as a point to make, because in many cases you can interpret a big blobby time result photoelectron spectrum in a number of different ways. And often you would just look at this potential energy surface and assume you knew what was going on. But it's only by calculating exactly how this instantaneous ionization potential looks that you can begin to define an observation window, and that's before you even take the Frank-Conlon factors into account in the ionization matrix elements. So from the full wave packet calculations, you can start to see actually how complicated things get. And so this state 2 here is the state we actually populate, and I'm just going to show a few different projections of this wave packet. So it's a full dimensionality wave packet, but as Fernando said, it's kind of hard to visualize that. So we'll just look at a couple of projections. And this is the asymmetric stretch coordinate that I'm showing here as a function of time. So you can see that you have kind of these bursts of dissociation as part of the wave packet moves along that asymmetric stretch coordinate. And you also have some kind of large part of the wave packet that persists along a relatively symmetric configuration of the molecule. And you can also see in this case, so state 3 is that higher lying state that we couple to. So you can see that we end up with some population there, and also population funnels down to some lower lying states. If we look at a projection along the bending coordinate, you can see that the motion looks a little bit simpler, but it's still not really looking very much like you might have expected from the experiment. And so we do see some oscillations here, you see, and at longer times some population kind of remains relatively stable in this bending part of the potential. But it really looks kind of complicated, and there's a lot of stuff going on. There's different ways you can project that. So we can also make a movie of that to try and visualize it a little bit better. So this is the three-dimensional coordinate space now as a function of time, just showing how this wave packet oscillates around. So this is this initial state that we prepare, this is the slightly higher lying state, and this is the S1 state that we couple down to as well. And so again, you can see it looks kind of complicated, and you can't really imagine how this is going to couple out to the observable that we actually look at. It also makes the point, again, that you know that wave packet dynamics in multidimensional systems are inherently complicated and potentially inherently interesting, but we really need to get a handle on this to sort of move forward. And so I pointed out that our observation window is small. So the first thing that we can do with this, and I'm going to be sort of brief here because this was only from last week, but we can take the full wave packet and we can send it just essentially through an ionization filter and just say we don't know anything about the ionization apart from what the instantaneous vertical ionization potential is. So let's filter the wave packet through that and see how much we can see. And so this is a slightly different coordinate space potentially, but essentially the top is showing the full wave packet here on that initially prepared state, and this is how much we can ionize. So at time 0, that looks nice, that looks fine. If we move to 250 femtoseconds, you can see immediately that the wave packet is spread over a huge region of coordinate space in the calculations, but the part we calculate that we can ionize is actually very reduced, very small. And again, if you go to 500, it gets even smaller. And so this is a good sign as to things are actually going to work out, because you can see immediately that much of the complexity that is really there, that's under the hood, just goes away in this observable. And so, in terms of interpreting the experiment, this is obviously a thing you want to understand. And in terms of an experiment where you aim at really measuring these full wave packet dynamics, then this is also a thing that you really need to get a handle on, because this would not be the experiment to choose if that was your aim, as it turns out. And so, yeah, finally, so these are also results from last week. So we've now started calculating the molecular framework photoelectron angular distributions in this case. So this now gives the complete picture where we have the full multidimensional wave packet, and we also have the full set of ionization matrix elements, so we can really do a full calculation to compare with the experimental results. And in that case, these are the lab frame photoelectron angular distributions that Vince has calculated. And actually what's quite interesting in this case is that it sort of verifies our very qualitative model, which is that the angular distributions don't actually change much as a function of the geometry of the molecule, in this case, in these time windows that we're actually looking at. But what really changes is the ratio of the population on these states. And so in this particular case, we really are looking at an observable that just maps essentially the electronic population dynamics moving between these different excited states. I wouldn't necessarily say this is a general conclusion that we can make, because it's going to depend on the exact details of the system we're looking at. But in this case, it's quite interesting, and it means that, again, you can now think about perhaps applying these kind of qualitative or semi-quantitative models to other systems without going through the full pain of doing the full dynamics calculations. Okay, so that's just summarising that. How am I doing for time, Gina?
You still have 10 minutes.
Oh, okay.
Less than that.
Okay, that's all about the experimental part. Okay, so again, an obvious statement. We can learn a lot from these experiments, but you really need careful input from theory to really try and gain full details. And I guess I should also point out that the symmetry-based modelling is a useful thing to start to do to try and understand some of the core physics, but you also have to understand what's missing from that calculation. Okay, so butadiene is what we're sort of working on at the moment, and this goes back also to why I had those rotational wave packet calculations at the beginning. And so we basically want to extend this technique that we've worked on for CS2 to looking at a system where we have very fast dynamics. So in this case, the dynamics are going to be sort of sub 50 femtoseconds, and a case where frequency result spectroscopy can't really tell us very much. So this is of course the reason you get into making time result measurements. These are the kind of questions you want to ask. And we're going to, butadiene's a nice molecule to start with, because it's kind of a prototype for a whole family of hydrocarbons, and it's also already well studied, so there's lots of existing experimental and theoretical work that we can fall back on. And so in this case, I'm going to start with some of the dynamics. So again, this is from Michael Skerman at NRC, and also Todd Martinez's group has done some work on butadiene back in 2009. And what's going to be interesting here are the kind of timescales that are involved. And so these are kind of projections of some of the key coordinates or key vibrational motions in this case, and particularly this carbon-carbon stretching motion, which gives you kind of an oscillatory behavior, and the period here is around 20 femtoseconds or so. And this torsional motion, which actually couples very strongly populations on the S2 state that we prepare down to a lower lying and dark S1 state. So this torsional motion you can think of essentially as leading towards the conical intersection that couples those states together. And so you can see, in terms of that motion, it's very fast and it's irreversible. You essentially see everything bending within probably 30 femtoseconds or so. There's a little period of stabilization, and then this red dashed line here is essentially when all the population goes down to a lower lying S1 state. So S2 is the state we prepare, S1 is the state that the population is sort of funneled down to. And this is fast, this is, well, fast in the femtochemical world. Not attosecond, obviously, but 30 femtoseconds here, 50 femtoseconds here. So those are the kind of characteristic times that we're thinking about. So we're going to do this experiment again. It was done on this coincidence imaging spectrometer, and we measure photoelectrons and photoions. We can pull out the time resolved photoelectron spectrum from that. Again, it looks sort of uninteresting. It's kind of a big blob and a sort of chirped band here that quite quickly disappears, as you expect from the population dynamics within 60 femtoseconds or so. And it has this kind of characteristic chirp. And if you look at that in an energy normalized picture, you can see essentially this dashed line follows is just highlighting the peak in the signal population in any given energy slice there. What's slightly more interesting is if you look at the tail of this band, you can see that it follows almost the same gradient. So there's very little dispersion in this wave packet. You're essentially seeing it funnel very quickly down a steep surface and a steep gradient of the potential energy surface, and with very little orthogonal motion that we see in the observable. If we look at the angular distributions, things look a little more interesting. Maybe you can reach your that. So this is the probe signal at the top here, just to show that there's no time dependence seen in that, as expected. There's no artifacts sneaking in. And then this is the pump probe signal for various different energy slices as a function of time. So this is 10 femtosecond bins here. And you can see it's a little noisy, particularly down at later times. There were technical issues there, which I can talk about in the questions if anyone's interested. But what you do see is that there are indeed strong changes in this observable. So you can see changes at the poles here, for example. You can see changes around the equator, particularly in this lower energy slice. There's this kind of beating around the equator. So there is a bunch of stuff going on, even though we see nothing, again, in the energy spectrum. And so if you get rid of the messy data points and you make a prettier picture of how those look, they look something like this. So again, this just highlights the fact that you can see this kind of, in some cases, beating around the poles of the distribution or beating around the equatorial region of the distribution. You can plot those in terms of the beta parameters. So in that case, you can see maybe a little more clearly the kind of temporal behavior here, in particular what looks like a beating behavior in the beta 2 in this lowest energy case. And again, the dashed line there is just the counts of the photoelectron spectrum, or the time resolved photoelectron yield, I guess was taken. And so in those cases, you don't really see any of these dynamics. And so if you plot everything up together, this is how it looks. So you can essentially see that over this main feature of the signal, which is basically the cross-correlation of the laser pulse, we're just putting population up onto this excited state. Laser pulse is about 40 femtoseconds in this case. And stuff is disappearing very quickly, and we're mapping that vibrational motion onto essentially the instantaneous ionization potential. So over that cross-correlation feature, we don't see much of a change in angular distributions at all. This is sort of, I guess, what we'd expect. But then further down here, when we're out of this cross-correlation region, we can see that some of these beats appear in the beta 2. And this oscillation period, again, is kind of suggestive of what we saw in the calculations. And you can also see that at later times, things get, is that a timing? You can also see that at later times here, there's a decrease generally in the beta 2 parameters and an increase in the beta 4 parameters. And I should say that the beta 4, they kind of look really noisy here, but if you do the same kind of plot with larger energy slices, you can convince yourself that at least this switching behavior at later times appears to be a genuine result of reproducible and not just a statistical artifact. Okay, so that says what I just said. I'm preempting myself. And so, can we say anything more about that? Again, the real question is, if you measure this experimentally, is there much more you can say? or do you really need to go and do a full theoretical treatment? From the timescales, you can at least say that these oscillations suggest some mapping of vibrational motions, and the step changes suggest that we're seeing the electronic population dynamics there, because we know or we expect that to give a significant difference in the angular distributions. And as I say, the timescales are kind of suggested from the experiment, but of course we so far, I'm missing a slide there, I think. We so far don't have really the coupling between these two. We don't have the ionization matrix elements that we now have in the case of CS2, so there's still a step missing in terms of this experiment, but again, it's looking promising. And so that's also just an example of the other kinds of measurements we can make in terms of correlated photoelectron spectrum with particular fragments in this case. And so looking at all of these observables gives us the beginnings of an experiment where we can really start to think about making multidimensional mappings of a wave packet, but we still really need to understand this coupling. And in this case, because we have a full set of ion data, which we didn't have in the CS2 case, we can also hope that we might start to gain further insight. And so from looking at the ion yields and the ion angular distributions, these can also give us some insights into the dynamics. Okay, so my conclusions and outlook. Just to say, everything's complicated. We've heard that a few times today. But we can now make complicated measurements which help to disentangle the complicated dynamics we were trying to learn about. But we do also need to understand this coupling. And that's something that really, at least in the femtochemistry world, and particularly from the experimental side of things, has been lacking up till now. So now we're really getting to the point with these kind of mature theoretical and experimental treatments where we can begin to couple these things together and hope to start learning and understanding the dynamics of larger systems. And to say that even more pithily, I have to say that time constants are not dynamics. In some cases, again, that perhaps they are when you have these well-separated bands, and one band disappear and another band appear, and there's a very clear signature of the dynamics